Hello, my name is Victor Wilcapi, and today I will present our paper titled A Multi-Objective Optimization Approach for Tuning Multivariable DMC Controllers. The presentation is organized into 4 sections. Section 1 provides a brief introduction to multi-objective optimization based design and DMC controllers. Section 2 describes the proposed methodological approach for tuning DMC controllers in multivariable systems using a multi-objective optimization framework. Section 3 presents the application of the methodology to a linear multivariable system with 2 inputs and 2 outputs. Finally, Section 4 summarizes the main conclusions. A multi-objective optimization design procedure consists at least 3 stages. In stage 1, the multi-objective optimization problem is defined. In stage 2, the Pareto front is obtained using a multi-objective optimization algorithm. In general, a MOB does not have a single solution, but rather a set of optimal solutions with different levels of trade-off between its design objectives. This set of optimal solutions is known as the Pareto front. This paper used the multi-objective evolutionary algorithm available at the URL shown on this slide. Stage 3 corresponds to the decision-making stage. To help the designer select solution from the Pareto front, several visualization tools have been developed, as shown below. To analyze and visualize the solution on the Pareto fronts, the multidimensional fronts visualization tool known as label diagram was used. This tool is available at the URL shown on this slide. The label diagram tool assigns each objective its own graph, as well as with each of the decision variables of the map. The vertical axis of each graph corresponds to the value of the norm select to represent the Pareto front, and all graphs are synchronized with respect to this axis. The horizontal axis corresponds to the values of the design objective in the objective space or the value of the decision variables in the decision space. Each norm offers a designer different characteristics of the diagram and provides different point of view. Point A represents the best solution for objective J1, but it is also the worst objective J2. The opposite occurs with point B. Point C is considered a compromise solution for the multi-objective problem. Model Predictive Control, or MPC, is a widely used methodology for handling complex industrial processes. The basic idea is that MPC predicts the future behavior of the process over a given prediction horizons and computes a sequence of control actions that minimize a select performance criterion. One of the most common MPC algorithms in industry is dynamic matrix control, or DMC, mainly due to its simple implementation and strong performance. DMC relies on linear model of stable open-loop system, use the state response to generate the future predictions, and assume constant disturbances over the prediction horizons. On this slide, we illustrate how future outputs are computed using past inputs up to the current time. The algorithm predicts the outputs across the entire prediction horizon, from time t plus 1 to t plus p. Here, G represents the sentence dynamics matrix. We can also include weighting factor lambda and alpha in the optimization formulation. This way allows us to penalize input movement and adjust the closed-loop behavior. Finally, the slide shows the resulting optimization problem that the controller solves at each sample time. Now, I will to present the methodological proposal. The proposed methodology addresses several important limitations in the existing multivariable control literature. First, scalability, applicable to complex multivariable systems with strong couplings. 2. Informed trade-offs, uses Pareto France and label diagram for guide parameter selections. 3. A multidimensional design approach where the designer can select the number of design objectives based on the depth of analysis required for multivariable process. To demonstrate the methodological approach proposed in this work for tuning multivariable DMC controller using a multi-objective optimization framework, we use the multivariable system shown in this slide. In this multi-objective problem, 4 design objectives are defined to evaluate system performance and control action independently. That is, without combining them into a single metric. This allows a truly multidimensional analysis to the problem without losing information relevant to the designer. Objectives J1 and J2 assess how well outputs Y1 and Y2 track their corresponding reference signal ESP1 and ESP2. For this, we use the integral of the square error. Objective J3 and J4 quantify the effort required from each control input using the integral of the square control action. Finally, to define meaningful bounds for the decision vector, a referent DMC controllers was first tunes. This helps reduce the search space and decrease the computational cost of the optimization process. To establish the bounds of the decision vector, we first tune a reference DMC controller. This helps reduce the search space and lower the computational cost of the optimization process. In this work, an unconstrained multivariable DMC controller was tuned, since the constraints are defined directly in the multi-objective problems. Table 1 shows the resulting bounds of the decision vector. This slide also presents the configuration of the multi-objective algorithm using to generate the Pareto frames for tuning the multivariable DMC controllers. Now, I will move on to the results and discussions. In the multi-objective optimization process, the Pareto frames and Pareto sets were obtained as shown on this slide. To visualize the Pareto frames and analyze the trade-off among the design objective, we use the label diagram tube with the infinite norm. This norm helps illustrate how much one objective can worsen relative to another. The Brown solution for objectives J1 and J2 show a clear conflict in controlling outputs Y1 and Y2. In other words, the solutions that perform best for Y1 are the worst for the Y2 because the green region lie on opposite sides on the Pareto fronts. Likewise, the yellow solution lie on opposite sides for objectives J1 and J2. Regarding the DMC control actions, objectives J3 show that the solution achieving the best performance for Y1 require a higher control effort. Objective J4 show the opposite trends. The solution that perform best Y1 require less control effort. The Pareto set presents the tuning parameters of the multivariable DMC controllers obtained through the multi-objective optimization process. It is linked to the Pareto branch such that selecting a controller on the front automatically highlights the corresponding tuning parameter in the set. In this slide, the brown traces the response of the best performing DMC controllers with respect to output Y1, that is, those with J1 less than 11. In this case, output Y1 is stabilized at around 300 seconds, while output Y2 reaches steady state at about 400 seconds. Similarly, the yellow trace represents the response of the best performing controllers for output Y2. Here, output Y2 is stabilized at approximately 300 seconds, and output Y2 settles at around 450 seconds. These bronze and yellow response correspond to the same color coding used in the Pareto branch shown earlier. To assess the trade-offs among the solutions on the Pareto branch shown earlier, 3 controllers were selected: PA, PB, and PC. The PA controller provides the best performance for output Y1, as it achieves the lowest value for objective J1 compared with PB and PC. However, it yields the poorest performance for output Y2, seeing its objective J2 value is higher than those of PB and PC as shown in Table 2. On the other hand, the PB solution represents the best controller for output Y2, as it achieves the lowest value of objective J2 compared with PA and PC. However, it also provides the poorest performance for output Y1 as shown in Table 2. We also tune 2 proportional integral controllers, one diagonal and one off diagonal, to compare their performance with the DMC controller obtained using our proposed methodology. As shown in Table 2, the DMC controller performs better in 3 of the design objectives, J1, J3, and J4. Finally, the selected DMC controller is shown in PC, and its performance is compared with the diagonal and off-diagonal PE controllers. It is observed that DMC controller provides better performance in controlling output Y1 than the PE controllers, as it achieves a shorter settling time and exhibits fewer oscillations. Finally, the conclusions. A framework for tuning multivariable DMC controller using a multi-objective optimization approach was proposed. First conclusion, the Pareto fronts show a clear conflict between system output solutions that optimize Y1 degrade the performance of Y2, and vice versa. Second conclusion, trade-off in control effort were also identified, illustrating how aggressive one DMC tuning can be compared to another. Conclusion 3. The Pareto set revealed how the NC tuning parameter directly impact controller quality. And based on designing preference and the information provided by the methodology as suitable, the NC controller was selected, achieving stable behavior with non-aggressive control actions. That is all. Thank you very much for your attention.